Hello everyone, welcome back to another lecture of machine design. In this lecture, we're going to be talking about this problem and working through it. A solid circular rod of diameter d undergoes a bending moment. Bending moment equals 1,000 pound force times inches, inducing a stress of sigma equals 32 m over pi d to the power of 3. Using material strength of 25 kpsi and a design factor of 2.5, determine the minimum diameter of the rod. Use table A17, select the preferred fractional diameter, and determine the resulting factor of safety. So first of all, let's first draw a diagram of this problem. We have a circular rod of diameter d, undergoes bending moment this, and it induces a stress of that. And this equation is from the form sigma equals mc over I. So we can know that it probably undergoes some bending like this attached to a wall maybe. And this induces a normal stress because when a beam is bent, some stress elements are under compression and others are under tension. Um, so we want to use a material strength of 25 kpsi and a design factor of 2.5. And we want to determine the minimum diameter of the rod. So first we have to know some key relationships in this formula sheet. Actually, this particular equation is not on our equation sheet, so it will be good if we memorize it or if we put it on the equation sheet. So the design factor or the factor of safety is ND, and it is equal to the material strength over the stress. So the factor of safety ND for any material with the material strength S subjected to the stress sigma is given by ND equals to S over sigma. So here, our ND is going to be equal to the material strength of 25 kpsi, which is equal to 25 kips, over 32 m over pi d3. And we can solve for d as being actually I decided to keep the S as an S for now, just to make things more simple, since later we are going to have to do a conversion factor. So double check that everything is right. And we plug in the given numbers. So S is equal to 25 kpsi, which is equal to 25 times 10 to the 3 psi, just to keep it in pounds. So plugging this value for S, we get that D is equal to 32 times the moment of 1,000 pound inch, 1,000, and a design factor of 2.5, so ND equals 2.5 over 25 times 10 to the 3 times pi to the 1/3. And this calculates to So D is equals to 1.006 inches. Now, yes, so we have determined the minimum diameter of the rod, and we now have to use table A17 to select a preferred fractional diameter and determine the resulting factor of safety. So here's table A17, preferred sizes for our numbers. So we have in terms of inches and in terms of decimal inches. So for this problem, we when it comes to selecting a shaft, we select one with the diameter equal to or greater than the calculated diameter. From the table A17, one can use fraction of inches or decimal inches. I'm using fraction of inches. We get selected diameter ds is equals to 1.25 inches. Under the same bending moment m, the bending stress on the shaft of diameter d nu can be calculated with that. So we can choose, we want to choose a diameter equal to or greater. So our diameter is about 1, so we have to try to choose one that's slightly more, which is 1.14. No, 1.25 or 1 and 1/4 in fraction of inches. So we're going to go back. All right, so over here, we choose our diameter as d nu is equal to 1.25 inches, and we have to calculate the new factor of safety. So factor of safety will be n nu. That'll be equal to the strength, which doesn't change, over sigma nu. Sigma nu does change. Sigma nu will become 32m over pi times d nu cubed. And this is equal to 32 times 1,000 over pi times 1.25 inch cubed. So the new factor of safety when we calculate this out is equal to first we have to calculate a new sigma is equal to 5215.189 psi, pounds per square inch, and thus nu will be equal to 25 times 10 to the 3 psi over 5215.189 psi. And this is equal to 4.79 as our factor of safety nu. So this concludes this problem. I hope this problem was helpful. So this deals with fractional diameters and also basically we determine the minimum diameter of the rod for a design factor of 2.5, and then we select a preferred fractional diameter, and then we determine the new factor of safety. So what is the point of all this? A preferred fractional diameter is a standardized size from a set of common fractional inch sizes like 1/16, 1/8, 1.1/4 inch, chosen for a mechanical component after the theoretically required diameter has been calculated. Engineers select a preferred size from this standard list to ensure that the final part can be manufactured efficiently and cost effectively while still meeting the necessary strength and safety requirements for the application. As you see over here, it's basically due to manufacturing and the standards that manufacturing needs. It will be incredibly hard to manufacture a diameter of 1.006 inches of precision. And it's unnecessary. And it might be even better to choose a higher diameter to have more strength. And 1.25 inches is more standard and more easily manufactured in that sense. So the new factor of safety that we'll have is actually larger, which is better. That's why we choose a diameter greater than or equal to the one that we have. Thank you for watching this video, and I hope it helped you, and see you in the next video.